digital image processing fundamentals. I've already talked about many aspects of digital image processing. Because this is a workshop on soft computing, I should say something about, is there any relevance at all of soft computing technologies in the domain of image analysis or image processing? And if so, then why I am motivated to use this technology for image analysis? The presentation will be grouped in the following manner. First, soft computing introductions, which have already had certain introductions. I will still give very brief introductions. I will skip some of the introductory portion which is built in this presentation, because in the lecture before me, Shushmita has given a good introduction to genetic algorithm. So genetic algorithm introductions portion I will skip, and rest of the things I will give a very brief. So this is the part with which I will talk about three different kind of soft computing tool and their synergic combinations. That means whether the genetic algorithm could be fused to fuzzy systems, neural network could be fused to scientific systems, so this is called a fuzzy or fuzzy genetic algorithm. Now, digital image processing plays an important role in designing the intelligent machine having human visual-like capabilities. Because you know the people are trying to develop a robot which can able to act in a human-like fashion. Their camera will capture the scenario surrounding it, that means the world scene, and from the world scene they try to analyze the situations and take the decision accordingly. So to develop such system, what is the basic criteria we need have to fulfill? The human visual system has property. Number one is capability of handling uncertainties due to measurement errors and environmental parameters. What do you mean by this? That means human visual system I talked to yesterday, that even in a dense foggy morning, you could able to recognize the human walking up to you. If it is almost dark, there is the lamp is not, there is only feeble light from the moon, still you will be able to recognize. That means whether it is the bright sunlight, whether it is the very dull lights, human beings have a capability of handling those situations very nicely. Efficiency, independent, class and type of input data. What does it mean? Human beings are equally efficient in handling pictorial data, numeric data, alphabetic data, or any other kind of data in equal A's. That means it has got no choice like a computer that has to be 0 and 1 format, something like this. So, the machine, if it wants to build, which can mimic the human being, should have those capabilities. That means it should be data independent. The flexibility and adaptability to incorporate the changes of its functionalities depending on the data characteristics. That means it should be adapted. Say in one situation, one kind of data it is handling and its efficiency is in the peak. Now, on the next moment, if the data type changes, its efficiency should remain in the same. That means what it has to do, depending upon the situation, its internal mechanism, the internal circuitry or the system has to readjust itself to handle the new situations. So this is the basic characteristic of human visual system. Because when the dynamic range is very high, it is efficient. Dynamic range is very low, it is efficient. Whether it is a foggy, it is efficient. Whether it is a clear, it is efficient. So every time when we are handling the situation in same age, it means our neural system inside our brain has got certain idea about the situation which is learned over the years, and accordingly it applies those ideas to readjust the neural network, visual neural network, to handle this kind of situations. Parallel distributed computing paradigm is a facility of interaction among the elements. As such, human brain having a network of neurons, millions of neurons in a network fashions, and they are interconnected, they do parallel operations. There is no denial of it, there is a lot of experiments are done. So, if the machine has to perform this kind of things, we have to have this kind of architecture to be present in the machine. And last, the robustness, ruggedness against the noise, distortion, failure of components has to be there. Because you know, as we grow old, lot of neurons are dying every day and few neurons are coming in. But our efficiency of doing day-to-day operation doesn't change at all. So how it is happening? Because failure of one or two components does not matter on the overall efficiency of the system. That means it is so redundantly networked. That means at each connections there are thousands of parallel connections exist. If one connection is disconnected, the overall efficiency will be deteriorated by one or thousands of parallel. That means nothing. So this kind of paradigm has to be there in a situation when we are trying to design intelligent visual machines. So desirable computing paradigm should have this kind of characteristics. So approximate reasoning, efficient searching and handling of numeric, non-numeric data. Soft computing paradigm is having all this kind of reasoning. So why I am going for soft computing paradigm? Because I am looking for such characteristics which computational characteristics which should exist. So that's why, and because I know this has got this kind of thing, so I have intended to use it. It has got capability of handling uncertainties. Fuzzy model is mainly used for the modeling of the uncertainties, approximate reasoning and tolerance to the imprecisions. What do you mean by tolerance to the imprecisions? Fuzzy sets. Have you had any introductory lecture on fuzzy sets? Okay. So fuzzy sets you have seen that it is basic capability of fuzzy set is to take the imprecise input, not the precise input, and deliver nearly perfect output. That means under imprecise situations, it can optimize the output in such a way that is almost near to the truth. Robustness with parallel flexible processing, which is having the tools, neural networks having parallel processing can do. If one of the network is getting disconnected, its operation efficiency doesn't change much. Delivering low cost solution. Just you have got the generic algorithm can do that, low cost solution, because it can reduce the competition. So these are the three capabilities which you are looking for to design a machine very near to having a intelligent visual capabilities or the present here. Besides that, many more things are required, but at least three things are available right now. Sorry. So, taking all this together, we can make a human decision making this kind of thing. So, as per the, I am taking the quote from the author of fuzzy systems, Fijade. He says that basic aim is to approximately precise solution to a problem formulated in precise input and description. It's a very nice quote. That means in real life situations, there is no precise inputs available. So we have to take the reality by taking the imprecise input as input and try to model a system which can give you almost precise solution. It exploits the tolerance of imprecision, uncertainty, approximate reasoning, partial truth to achieve the tractability, robustness, low cost solution, and close relevance to human vision, human decision-like system. This is the quote of Jade. When he first coined the fuzzy set theory, he says like this. This is a philosophical quote, but actually it came true when he was implemented. The soft computing is a collection of methodologies that work synergistically. What do you mean synergetically? That means they are not competing each other. They are actually helping each other. So synergetically they are. Methodology is one of the another reflects the basic guiding principle of soft computing as follows: to exploit the implication with that field. So I'm just this is in general. They are also telling the soft computing community is called the machine IQ. That means if you use those technology to develop a machine that will be more intelligent than if you design a machine with conventional paradigm. So the major tools of soft computing are normally still there. Major tools, there are many minor tools of course. Major tools are fuzzy logic, neurocomputing, genetic algorithm and rough sets. I will cover up the first three. Rough sets has already been covered by, I think, Shankar has completed. So, fuzzy logic, the algorithm for dealing with imprecision, neural network, the machinery for learning and carpeting, GA for algorithm for search and optimization, and RS for handling impreciseness, uncertainty arising from the granularity of the domain of this course. This is already been covered, so I am not going into the details of it. Now, fuzzy sets, as you know, in contrast to normal sets, what is the difference between the fuzzy sets? As you know, the normal classical set we depicted by second bracket like this. The mu, it contains 0 and 1. This is a classical set. That means it contains two quantities, 0 and 1. And on the contrast, fuzzy sets is depicted by the third bracket, 0 and 1. What is the difference between the two? The difference is that the second set, the fuzzy sets, contains all possible values from 0 to 1, including 0 and 1. So, if we graphically represent that thing, in normal sets, there is two sets, that is 0 and 1. And in fuzzy sets, is gradually increasing to 1. That means it contains all continuous value, all real value between 0 and 1. This is called the membership function and has all possible values of membership function in the first sets. Now, I am not, in this context, I will tell you a little bit out of this, that now many people started questioning about the membership function itself. They say it is a fuzzy sets, then membership function should be fuzzy. Why should be strict one value? So that gives birth to another type of fuzzy sets type 2, where the membership value is having a range rather than a single value. So this is a current development nowadays. We are now working, one of our students working on it for an application. So the fuzzy sets is a generalization of the classical set theory, greater flexibility in capturing the faithfully various aspects of incomplete and imprecise situations. Let us set one example here. Here, there is a statement. Dr. Reshma told me that she will be coming at 4 o'clock, around 4 o'clock or 5 o'clock. What does it mean? Will it mean that if she comes 1 minute to 5 or 5 minutes, 5 past 1 minute past 5, will not be acceptable? It is acceptable. We in normal say always using that I will be coming around 5. Means nearly 5. So instead of a single 0.5, there is a band. Now, as it is going precise and precise, the band is getting narrower and narrower, it becomes one is classical sense. So in normal sense, this is always happening that we never get a precise input. We are getting inputs which are having a band. So with these inputs, how we can handle the situation, that is the beauty of the fuzzy sets. Now fuzzy sets is having different kind of membership function concept. It is called S-type membership function. It is also a RAM-type membership function. And there are various other kind of membership function exist. It's called the pi type and RAM and other type of membership function. So is the example of it in introductions. So membership function determines how fuzziness in the fuzzy set contains. Now, in one seminar when I was talking about these things, one fellow stand up and asked me, what is the difference between the probability and fuzzy membership function? The fractional number, possibility and membership. Then I have a very classical example, just give it. There is two bottles. One contains honey, one contains poison. Another two bottles, one contains honey, one contains poison. Now, on one bottle, it is written that the probability to be honey is 0.9, and another bottle, it is written membership of honey is 0.9. In the other bottle, probability of honey is 0.1, that means it is poison, and probability of honey membership is 0.1. Now, if I ask somebody to pick up a right kind of bottle of honey so that you are not dying, then what bottles you should pick up? I will pick up the membership value 0.9. Why? Because it is very close to honey. And probability 0.9 means if I am unfortunate, 0.1 poison I will take. So this is a clear-cut demarcation between the probability and membership function. That is what is the probability gives you the possibility of an event, and it gives you the closeness of it. So understand? Now I have shown you yesterday the uncertainty in this process. That I have shown you a edge picture where is a gloomy picture over there, and on the right side there is a clear edge of a artifacts. Okay. Now in a dark situations, finding out the edges even by human being is very difficult, because the variation of intensity is so low, you don't know where the actual variation is situated. Even in the cloudy situation, if I ask you that what is the extent of a cloud, can you say? Because it is getting thinner and thinner and smarts to blue sky. So in that situations, if I do the image processing, I have to face lot of uncertainties in locating that thing. So in that situation, the area, perimeter, corner, line, etc., which is very trivial in two-tone sense, that means when we see the textbook, it is a black and white, nothing, there is no uncertainty. But if it is a multi-level, the uncertainty arises. So developing a decision rules groundwork for describing and interpreting and classifying the image of a sub-region becomes a difficult task. Since those regions of image are not always clearly defined, an uncertainty can arise from every phase of the thing. Now, one of the basic advantage of the fuzzy set theory is that we are not discarding any possibility at the beginning. Say in a situation of clustering, the normal clustering say this point belongs to this cluster, this point belongs to this cluster. This is gone. Now, if it is overlapping regions, due to my mistake, I am misclassifying one of the points to the wrong class. In fuzzy set, that doesn't happen. In fuzzy clustering, what we does, we say membership of this point to belongingness of this cluster is say 0.9, and membership values of the same point belonging to the other cluster is say 0.3 or 0.2, 0.1. What is the advantage of it? Now, after that, I am doing some other processing. Both things are available at my hand. If something erroneous thing is coming, then I will go back to the earlier decision and says that membership function 0.3 was there still, so we should consider those things as valid points. I am giving a very real life examples. We are given a task by the DRDO to find out the runway and other things, the runway and the roads from the remote sensing imagery. Now, as you know, width of the road is very narrow in compared to the total scene. It may contain 1 or 2 pixels. sometimes there is some shadow, trees, and it is getting disconnected. Now when you are trying to find out the stretch of the road, we didn't get everywhere. Sometimes the road is there, nothing is there, road is there, nothing is there. So what our strategy we took the fuzzy model of it. At every point, we try to see from the signature what is the membership of being road here, what is the membership of non-road here. So after doing that, we get certain points which is actually depicted as non-road because of our experience that road cannot be like this. It could be a straight way, straight, long and continuous. So by checking the second possibility, we can arrive at a situation where we could able to join those points as a road. So compared to the conventional system, if we commit a mistake at the first stage of the processing, it will continue and it will continue to grow. And in fuzzy sets, we are keeping open all the options for the subsequent stages, and final decision is taken at the last stage. So total overall error could be reduced to a minimum extent. Now the definition of fuzzy sets like this, F is a fuzzy set. It contains the membership functions mu f, p, q for all the values p and q from 1 to q. The membership function of S type is defined like this. And there is another kind of membership function now, Z function, which is a complementary to the earlier membership function. It's called 1 minus S, that means 1 minus the complementary sets. Fuzzy entropy is defined in the same way, very similar way to the normal entropy, Shannon's entropy. P log P, we normally know the Shannon entropy, that is the probability is P of an event, that Pi is an event, and the summation of Pi, log Pi is the entropy of an event, you know. Similarly, here the entropy is defined as 1 by n ln2, this is a normalizing factor, and summation of S n mu p s. And S is defined as this normal entropy, that is mu f pq log mu f pq minus 1 minus mu f pq 1 minus mu f pq. Why the second term? Second term is because of in the normal entropy there is one term. In fuzzy entropy there are two terms. Why? Can you say anybody? Because we are making a universal formulation. If I take the bright as 1, dark as 0, will be one formulation. If we take bright as 0, dark as 1, there is another formulation. But if we take normal sets and complementary sets, it will always true. So that's why it is more generalization than the normal entropy. So entropy is a measure of informations, the greatest ambiguity of the image, and indeterminacy in making the decision whether there is an individual pixel is black and white in collection of black and white. That is the entropy considerations. And there are another uncertainty arises due to this digitization. I told you yesterday that digitization is so, if it is very dark, then the picture quality getting down. So digitization means the spatial, I will say, the sampling. There is some uncertainty in the spatial sampling also. So there are two parameters, entropy and geometrical uncertainty. Normal geometry, in the school we have seen how we can make we can formulate the area, perimeter, etc. This is very straightforward. Length multiplied by width. Length plus that is the width and heights, if you take together, multiplied by 2, it will be perimeter, etc. But the situation is not that simple in the case of a multi-level things. That means it's not a black and white. So in that case, the area and perimeter is defined as sum of the membership function, that is area is defined as sum of mu. That means in a very crude sense you can say it's a cluster. Sum of mu means all points together. It will give rise to a total number of pixels. And perimeter is a difference of it. Difference of it means if there is a black and white, difference is 1. If there is a line, the difference is 1. But if it is a grey level or the multi-level, the difference will be membership function. That means it is a graded area, graded perimeter. That means if you can imagine that if it is a tabletop, that means all heights are same, then perimeter nothing but this plus this plus this plus this. If it is a undulation, that is some of the yields are there, what will be the area? What will be the area? It is a weighted average. What is the perimeter? That will go this way and that way. That is nothing but the difference. So this is the difference.
What is TI?
Which is TI is its frequency. Tij. That means say level 1 and 2 has happened 20 times. So every time I have to compute. So I compute once and multiply it by 20. All the same. That is from the histogram. The Tij is a quantity derived from the histogram. Sorry. And actually we have used this formula for an enhancement algorithm. We have developed long back. Many people may not have born that time. This we have published in 1986. The first paper, automatic enhancement using fuzzy. So there we use the compactness parameter, that is area by perimeter square, as a fitness function or like this. Now, as I told yesterday, I have shown you the parametric form of enhancement. That one is because the logarithmic, one is exponential. I have shown you that C r to the power gamma y is equal to. So by changing the values of gamma, we can generate this. It can also be generated S and inverse S. This is the maximum possibility of function one can think of for nonlinearity, for image enhancement. So what we have done, we have taken all the 4 functions, and with these functions can be characterized by this kind of equations. The first functions, fx is equal to ax square by 1 plus ax square. This is nothing but a log function. Second function is S. The second one is S function. This is the inverse S function, and this is an exponential function. Now, all these things that if we thought of a situation that there is a camera in the remote places, and we have to control this camera every time, because if it is a surveillance camera, sometimes it is dark, sometimes it is very bright. So depending upon that, it may be flooded, it may be underexposed, overexposed. So how to control that in a remote platform? Human being cannot sit over there for day long and try to adjust it. So for doing that, what we have done, we are trying to develop an algorithm that given a situations, particular situation, capture it, whether the machine can decide which function you use for a part to get the best quality photograph which could be transmitted back. Actually, this idea was generated in USA when they sent the Mariner mission from that, because they used to send photograph. If it is a very bad photograph, the processing at the art station will be very difficult. So little bit of processing is done, but they have not published anything. So we published that things where we are first the selection. First of all, what we have done, we select one function out of 4 functions and go on changing its parameter value. If we change parameter value, the shape of the function will get changed. For different changing of parameter value, we compute the compactness value of the whole image. Our idea was that if image is best enhanced, it will be very compact. If it is not enhanced, it will be very dispersed. So with that idea, we do that, and that was myself and Professor Paul. We published it in 1990. We did it in 86. It is called automatic enhancement by fuzzy set theory. So the algorithm was like this. That was an initial image, and the machine itself decides the function and to generate the automatic enhanced image. We have not done anything. The algorithm has done it. So this gives you an idea that if we exhaustively search the space of all possibilities, we can able to end up with a best possible solution. But basic problem is that how much parameter selection we can tolerate. Because a parameter value say 1 to 10, whether we should take 0.1 or 0.01 or 0.001 to have the best possible solution. Because of the limitation of computation, we have taken very discrete selection of it. Now, to overcome the situation, same problem was tried later on with a genetic algorithm version. So, genetic algorithm, I am not talking anything about the things. Just now we have heard, so I am just keeping all these things. Yeah. So here what we have done, we took the same thing. We formed a chromosome with 4 different functions. One chromosome, the function 1, function 2, function 3, and function 4. This one chromosome comprises of 4 functions. And function means its parameter. Say it has got 2 parameters, AB, then AB will be concatenated to form a single function. This kind of mating pool is met. One of the best things beyond our imagination, we found that we are trying to find out which function was best. Okay? And that picked up that function, and with a particular parameter value, it will be best. But what happened ultimately, we show after several iterations, it generates an optimal function, which is not an individual function, it is comprising all the functions together. So certain portion it mimics from one function, certain portion it mimics from other functions. So I am just showing you the results here. This was the blood chromosome. We got it from University of Maryland. So you cannot see anything rather than the blocks, but it has got 4 arms. Now, the same thing, it is go on by this algorithm, that means selection of, with the genetic algorithm, selection, nutrition, etc., etc. And every time we are checking its compactness, whether it is very compact or not. And we are trying to find out the global optimum. So with that, you can see after 15 iterations, it has got a clear shape of the normal chromosome. After 20 iterations like this, after 25 iterations like this, and after 30 iterations is almost the chromosome. The thing is, to search this, we have reduced the search space by order of 2 to the power 100. Can you imagine how much it is? So, if you can reduce the search space by 2 to the power 100, it is almost instantaneous. And the result was almost astonishing, beyond our imagination, how the best result could be obtained by so fast. So this is a glaring example, our first example of fuzzy sets, how it can be done with the fuzzy sets. Secondly, how it can be further improved with a fuzzy genetic model, that means genetic algorithm property is being added to fuzzy sets and to have a very fast solution at the extreme. So this is the first example. Second example of the neural network. So neural network, I think somebody has covered already, yes?
Professor Bose.
Yeah. So this is not relevant here. Human intelligence discriminating power is mainly attributed to the massively connected neural network biological neurons in the human brains. Do you know that how the human being is learning? And we are storing our things in memory. Actually, when a child is born, then there are millions of neurons are connected randomly to each other. Now, as it grows, say first, how the child first recognizes the the sound of his mother. Then he recognized the face of his mother or father. Now these are the first two processes of learning. A child started doing it. Now as it starts doing it, that means when it's first sound, listening sound, the corresponding auditory neurons are getting normalized or regularized. So randomness is certainly slowly removing. Then his visual neurons started forming. And after certain years, 2 to 3 years, mostly the neurons are getting regularized instead of a randomness. The fellows for which unfortunately it is not getting regularized, they become epileptic patients because they are due to the random connections. Some inputs are coming randomly from somewhere which is not to be there, and the brain started functioning randomly. So so that the knowledge which he gathers from the child is being stored by the network configurations converges after years. That means becomes stable. The network combination stored the knowledge. That means massively connected neurons with certain configuration gives you certain knowledge. So this and the weights of the one neuron is connected to the others is connected by certain weights. The weights will give you the idea about the overall configuration, which dominates, which will not dominate, etc. So it has got a adaptivity capacity, adjust itself to the environment. You know, if you just get a massively parallel neural network, you just go on cutting one after another, you will see up to some extent the operation remains unchanged. That means those connections having a very weak link, the weight is very low. That's why whether it's connection, physical connection there or not, it hardly matters. So it has got adaptability to the environment and stability with that. Its speed is definitely very high due to the massiveness. Fault tolerance is there, that I told you. The ruggedness and failure to the components, that means due to the so highly redundant combinations, is rugged. Optimality, the classification, you know, the neural network can classify optimally to the best extent. So these are the major characteristics of the neural network. Now, the first neural network was given, the simplest one is the perceptron, that was the inputs, and so this just the sound, the weights, similar one layer perceptron. This things in the perceptron, we are using this threshold functions. Weights are for the different inputs and different weights are there, and there is the thresholding mechanism used for final decision, that is output. And threshold is normally sigmoid function is used. All these things you must have heard in the neural network sessions. So this is the multi-layer perceptron. Now I am going to the applications. So we have done a little bit of application of neural network. Two applications we have done. One is the classification of the massively distorted neural fingerprints. Now in fingerprints, in general, there are 6 different kind of fingerprints available out of, if you take the fingerprints, millions of fingerprints together, you see 98% fingerprints will belong to this 4 class. Besides that, there are 2 classes, accidental, and there are 2 other specialized fingerprints. I am not going to tell you all these things. The things are the twin loop, that is, there are 2 loops. Here 1 loop, and another loop. That is, 2 flow are going, one of this is called twin loops. And there is old, that means the flow starts from one direction, go to the top and go the other way. So there is a delta in between. Is that called the delta mix? There is a right loop, that means from the left to right and go back to right. And there is a left loop from left to right and then go back to left. And there is a dented arch, that is arch kind of things, comes to top and goes down, and there is a train. And there is a normal arch, and dented arch is very sharp, and this is a gentle. So these 6 types of fingerprints are major class, covers everything. The problem is, just like your UDI, many people are, you cannot recognize many people, the people themselves cannot recognize themselves from the pictures. So it's a very bad quality picture. So this kind of fingerprint is also being corrected. So one of the major thing is, these are the four things I have told you: the loop, arch, fold, accidental, mixed, and composite. These are the major class of fingerprints we are encountering. The problem is, when we are doing the fingerprint classification, you know the fingerprint of all human beings are unique. Now, if there is a 1 million fingerprint database, and I am asking that whether this my fingerprint is there or not, how to do it? One of the ways, they are one matching my fingerprint with 1 million fingerprint. It will take years. Okay? So it will not help. Now, one of the way of doing it, that is, it's called the structured way of keeping the fingerprints. That means, if there are 6 different classes, if I just divide the 6 different classes of the 1 million, then each will have almost 100,000. 100,000 or 150,000 of each. Like 150,000, if I compute how many regions are there, region varies is there. So density of regions are there. It is varies from human to human. So regions. Then there are some minutiae pattern. I am not going to detail. There are some disconnections, some looping, etc. on the region itself. So there are regions. So this way, if you can divide the whole fingerprint in different classes, subclasses, then maybe in one subclasses, the fingerprint may be of the order of 5,000 or 6,000. This is quite you can handle it. So in the first place, we have to do the correct recognition of the class itself. So how to do that? Now we have proposed a method where we use a method like this, that we take the fingerprint and there are 8 directions at 45 degree, and each directions we are taking a strip. Okay. So in a fingerprint, we are taking a strip horizontally, vertically, this angle and this angle. So on these strips, we are getting certain data, 0 and 1s. On that, we are computing the Fourier transform. That means we are computing Fourier transform in 8 directions. So this becomes a feature for computing that. So what we are doing, this feature extraction is 4 strips. 4 strip means 8 direction means 1 strip, this is 2 strip, 3 strip, 4 strip. Means 4 directions. In 4 strips, the fingerprint sub-images having fixed width and horizontal, 2 diagonal directions, etc. The strips are selected, passes through the core area, and these strips are so selected, it should pass through the core area, means in the middle. We cannot take the strips here, but it should go through the middle. Then we compute the Fourier transform of the sub-images, and a 4-layer MLP classification scheme was used with the 64 multiplied by 4 inputs of noise. That means 4 directions, 4 inputs. So I can show you the images of it. This is a multi-layer perceptron we have used. That is the 4-layer. Say the FFT of the fingerprint of right loop, you can see the top. This is the left loop. This is twin loop. This is a plain arch, and this is the old. Now, these are the FFT components at the directions, at the 4 directions. Now, if this is used as feature, and this feature is used as input to the neural network, and if you try to in the first of all, we are taking the clean neural fingerprints, say 100 of each type, and compute it. For 100 each type, first of all, we compute the feature and take the average of it, the average feature how it looks like. Then from the 100 features, we try to learn them, the 400 fingerprints randomly. Once it is stabilized, then we started giving this is the histogram of each things, the feature histogram, all the looks, and that is further compressed feature matched like this. And when we take the fingerprint of, this is very common, cut mark. There are many people having the cut mark in the hand. So if there is a cut mark, there is a confusion of classification. We are trying to see whether cut mark, this smudging, is called smudging. Previously it was with the ink, so smudging is done. And under inking, smudging, over inking, etc. and random noise, all these things was given to the inputs after learning. And we found that with the proper learning, we could able to recognize all types of fingerprints with the accuracy of 80%. That means this was done with a view how to do the massive screening of fingerprint database, which is of the order of million, to a good extent, so that we can reduce the computation time to a good extent. So this is one of the examples of fingerprint classification by neural network. And next thing, the last example I would like to give you. Is it over? Time? Time is there? Dr. Reshma, is it okay?
Sir, actually, I need to make an announcement for this.
Actually, you should do that.
I think before the people leave, there's a slight change. I think Professor Mitra, she is not coming in the morning slot. So that will be replaced by Professor Muri. And later on at 2:30, Professor Mitra will come.
Okay.
So this is a slight change.
So this is the last application. This work we did in 2003. The hybridization of HC2's application to remote sensing. Here, what we have done, we took a remote sensing image. Now, in the remote sensing image, normally non-natural image, there are a lot of texture components. And as you know, the texture is having a different looks if we change the scale. Just go to the Google map. You see the Google map of Delhi. In the first place you will see there are some spots and there are rivers, etc. There are some spots here and there. Now if you just go on increasing, slowly the buildings are appearing. So texture is getting changed from scale to scale. That is the Sports scale. If you go on fine scale. So for remote sensing analysis, the feature has to be multi-scale feature. Then and only then the analysis will be close to the perfect. So for that, we used a multi-scale feature mechanism by using a multi-band wavelet transform. Have you heard the wavelet transform? Everybody has heard it, I think. Wavelet transform is normally dyadic, it's two. If it is, there is a special type of wavelet transform which has got multi-band. We call it the in-band wavelet transform. We use 4-band. The idea of multi-band wavelet transform is that if it is a dyadic transform, it is horizontal and vertical. If the image is getting slightly shifted, then results will be different. In the multi-band, this is not only horizontal, vertical, there will be 2 cross components. If it is 4, if it is 8, there will be finer things. So there is a rotational invariancy embedded into the system itself. So that's why what is the motivation of using multi-band transform we have used. So after using multi-band transform, we do the adaptive decompositions. One of the problem of the multi-band transform is, in the first level decomposition will be 4, the second will be 16, third level 60, fourth level 256. So feature is exponentially growing. Now, which kind of feature should we take? We are taking an adaptive strategy. Normally, for a D level decomposition, it should be m to the power d to the power 2. Okay? That means if it is a 3 level, that is n is 4. If it is a 3 level, 3 square 9, 4 to the power 9. This kind of features is there. So, we have taken an intelligent strategy of adaptively selecting features. What strategy? We have, in our algorithm, we have considered those bands. First of all, we show the decomposition. This is the decomposition. In the first level 4. Then, in the second level, it is 16. In the third level, it is 64. Now, whether we should take everybody or not, we go on decomposing this number. To handle these things, what we have done, in our algorithm, we have considered, we should consider those bands which contains about epsilon 1% of the parent bands. That means we are starting from here. In a tree fashion, we are decomposing. When you are decomposing it, we are getting 4. Now we are comparing all the 4 with the parents, how much energy has injected to the particular things. If it exceeds epsilon 1%, that means 2 to 5%, then it will be a candidate for further decompositions. It is not, stop. Secondly, contains more than this percent of the parent bands and further decomposes band if at least it contains 50% of the total level. So first of all, we are considering this situation in a tree-like situations. Therefore, first of all, this is parents. This has to satisfy number 1 condition is 2.5%. It is a heuristically we have selected after experimentations. And secondly, even if it is 2.5% of the clearance, whether this contains the total energy of this level, it contains 50% of the total energy of this level or not. If it is there and all the way, it will be candidate for further decompositions. Otherwise, stop. So by this strategy, is called the clipping strategy, we could able to reduce about 40% of the total features if we don't use it. It's called adaptive strategy. This was very new, and that's why this paper was accepted at the first instant. So this was the filtering in the first, the nonlinear operations done in a classification, and last bit the clustering method. To do that, we use a evaluation strategy. It's called a beta factor. For any clustering algorithm you see, there are different measure yardstick is there. One is the beta measure is called. That is called the total variation within class and across the class. If the ratio is more, then that means within class variation is more, across the class variation is more. When within class variation less, across class variation more means it is more compact. That is, more things are compacted in a class and separation is very large. So, what was that? This was the IRS data. This was the Bombay dockyards, etc. It does not come very nicely. Here is the dockyard and there is elephant caves, etc. Now, this has got 6 classes. That means turbid water 1, 2, habitation, vegetation, concrete and other structures. So depending on the 6 classes, we are getting the cluster like this. That what is the your concrete structure, and if you see vividly, you can see some black spots here. Yes, you can see there is some not very uniform in color. The black regions are the depth is more. When the depth is more, it looks black. When depth is shallow, it looks slightly fainted. So these 2 things can be demarcated, turbid 1 or turbid water 1 and turbid water 2, etc. So the beta factor was 8.1 with the 6 classes, a normal clustering algorithm. When you use the neurofuzzy classification, that means a feature is evaluated by the neurofuzzy technique, the classification was increased by at least by a factor of 15 to 20%, that is 8.2. Okay, so 0.1 increase is very high, we say. And you can see, if you see the two pictures together, here there is a lot of overlapping things. Here is much less overlapping. You can see the much clear segmentation was available. Similar case we have applied to the Calcutta picture virus data. This spot data, French satellite. So these are the river, Hooghly, etc. And there also 7 classes. The conventional algorithm gives 3.277232, and with 7 classes, it is habitation, concrete, other structure, vegetation, brick and roads, and turbid water. There are a lot of ponds are there. There is turbid water is there, and pond water is there. There are 2 different water classes there. And it is the East Kolkata area. So when we are doing did the neuropathy evaluation for that technique, we got a much better, much clearer cluster of this meshy land anomalies. So this is the 2 examples by which we can see that the conventional from the, instead of conventional, that's one of the examples I just gave you. That is a road that where the structure is narrow. The decision making based on 1 pixel, then all the problem comes. And secondly, when the demarcation boundary is not very clear, then sometimes it gives you larger boundary, sometimes it gives you smaller boundary, not near to the actual reality. So, neurofuzzy model can handle those kind of situations because fuzzy is uncertainty and neural network learn from the known scene. So, it can able to handle those situations. So, research activities of these things are, you know, it's about when we started working on this soft computing tools around 86, it's around about 30 years now. So that time nobody dares to do that, but we tried these things. We see happily that many people have started using it now. So with that things, I will conclude my talk. Thank you for your patience, and you will tolerate me for 2 days.